Hi everyone, in this video we're going to look at Chapter 7. Chapter 7 deals with symmetric matrices and quadratic forms, and 7.1 specifically is diagonalization, so that word coming back, of symmetric matrices. Now, at the beginning of Chapter 7, there's like a page and a half of an application to the real world, like where this is used. It's pretty cool. Deals with satellites and imaging, multi-channel image processing. I highly recommend giving it a read. It's super interesting, and just it's always good to see where what we do in this class applies outside of this class and apparently in space. So cool stuff. Give it a read. It's big recommend. So we start out the section with a definition of a symmetric matrix. So symmetric, we saw previously where two matrices are similar to each other. So don't switch up those definitions. Similar is different than symmetric. So a symmetric matrix is a matrix such that its transpose is itself. So if you look at this first matrix here, this is symmetric because the 1, 0, if it pivots down, and the 0, 3 pivots up, right, that is, there's 0, negative 3, that is the exact same matrix, but the one right below it, that one is not symmetric. Take a look at it, see if you can figure out why. And then with the second matrix, 0, 1, 0, that becomes the first column. Negative 1, 5, 8, that becomes the second column. 0, 8, negative 7 is the third column. And then similarly, this matrix, while it looks pretty good, it is not symmetric. And then you got two more examples there that you can take a look at and see why the top one is symmetric and the bottom one is not. In example 2, a lot of the work is done for us, so the work is going to be in processing and comprehension of the relationships here, so that's what I want you to focus on. We have a matrix, we have a matrix A that looks like that, and then first thing to notice, 6, negative 2, 1, 6, negative 2, 1, negative 2, 6, negative 1, negative 2, 6, negative 1, right? That is symmetric. That matrix is symmetric. They've got the characteristic equation, it's factored, and then the eigenvalues are listed with the corresponding eigenvectors. Okay. Now, what I want to so that's some stuff that we've already seen way back in Chapter 5. What I want to first make a note of is that those three vectors, that set v1, v2, and v3, they form a basis for R3. Right? We've seen that in Chapter 5. But the next thing to notice is they are also, also orthogonal. So take a look at them. Pause the video if you want to check and make sure. They are also orthogonal to each other. This vector, and that vector are orthogonal. Their dot products are all equal to 0. So then the next step is if you normalize them, meaning divide by their length, give them all a length of 1. If you normalize them, then we'll call them u, since they're all unit vectors. u1 is negative 1 over root 2, positive 1 over root 2, 0. u2 is equal to negative 1 over radical 6, negative 1 over radical 6, positive 2 over radical 6. And u, that's a u, 3 is equal to a bunch of 1 over radical 3's. Like that. Okay. If you normalize them, those vectors, and then the corresponding decomposition, the PDP inverse, so if my P matrix is u1, u2, u3, so it's that orthonormal basis, then the diagonal matrix D8, 0, 0, 0, 6, 0, so consisting of those eigenvectors or eigenvalues up above, then the significant fact here is that if then let's say then A is equal to P D P inverse, but P inverse is the same as P transpose. P inverse is equal to P transpose. and that is, since P is square and it has orthonormal columns, P is an orthogonal matrix. P inverse is the same as P transpose. So if you are like not seeing that connection, that's okay. What you can do is look back at section 6.2, okay? And that's where that relationship was established, okay? So P inverse, I don't need to do any additional computations or even button pushing to find that. It is just the same as the transpose of P, all right? And again, the significance also here is that when that P matrix is orthogonal normal vectors, computation becomes simpler. It becomes more efficient, whether doing it by hand or a computer doing giant matrix computations. And all of this started with, way back at the beginning, A being a symmetric matrix. Now we have a theorem, and we'll do a proof that generalizes one piece of the example from the previous slide. So the theorem being, if A is symmetric, then any two eigenvectors from different eigenspaces are in fact orthogonal to each other. Okay, so that's what we are going to prove here, that those eigenvectors are always orthogonal. Let's go through a proof. Okay, so we're going to say let V1, so we're going to define two eigenvectors, V1 and V2, be eigenvectors that correspond to eigenvalues lambda 1 and lambda 2. Lambda 1 and lambda 2. Oops, forgot my subscript. There we go. And then we have to show that V1 dot V2 is equal to 0, that they are orthogonal. That's our goal in this proof. And the way that I'm going to do that is by kind of a chain of equalities. This is equal to that, is equal to that, and then the goal is to understand the jump from each step to the next, okay? And so what we're going to start with is we're going to say, let's say that I have that dot product. I don't know what it's equal to yet. I need to show it's equal to 0, V1 dot V2, and I want to start out just by multiplying it by lambda 1. So I'm scaling that dot product that I want to show as 0. Okay, so that's my first step. Lambda 1 V1 dot V2. Well, let's write that a little bit differently. Instead of writing it as a dot product, let's group lambda 1 V1 and transpose it so that I can write it as regular multiplication. So the dot product is equal to the transpose times the other vector. Now, let's make a substitution here. What is lambda times v? Lambda 1 v1? Well, that is just a v1. That just scales right? That's the eigenvalue definition, basically. A v1 transpose times v2. So we're making a substitution. A v1 equals lambda v1 is our initial chapter 5 relationship for eigenvalues. And so I'll write a reason here, since v1 is an eigenvalue. Okay, there we go. All right, now, and then what else are we going to say? We're going to say that this is now, again, so still equals, but I'm going down to a new line. This is equal to, let's see, my next step is I am going to kind of distribute that transpose in, right? And it's going to change the order. V1 transpose times A transpose. So I'm taking that T, bringing it in, right? Then that changes the order. That's times V2. Okay, now what are we going to do next? Let's change our grouping. This is V1 transpose times A V2. V1 transpose times A V2. All I did in that step, change my grouping. Well, actually, I did two things, right? Here I have a transpose. Here I don't have a transpose. Now, why do you suppose that is? Well, what were we given right at the beginning of this theorem? If A is symmetric. So my reason here, since A transpose is equal to A, it is symmetric. Okay, so that's why I can just piece out, erase that transpose there. All right, next equality. Oops, let's go back to blue. This is equal to V1 transpose times lambda 2 V2, right? We're substituting that eigenvalue relationship. AV2 equals lambda 2 V2. And this is my reason here, since V2 is an eigenvector. V2 is an eigenvalue. Cool. All right, so we are getting somewhere. I swear, there's like 17 equal signs here, but we're getting there. Next, I am going to take my scalar, that lambda 2 in there, and pull it out in front. So I'm going to commute that scalar out of the parentheses. So lambda 2 times V1 transpose times V2. Lambda 2 V1 V2. All right, and this is equal to lambda 2 times the dot product of V1 and V2. Okay, so I did my V1 transpose times V2 and then rewrote that as a dot product. Okay, so what the heck does all of that do? I think this is a really cool proof because you just kind of, this eigenvalue here works its way through and then disappears for a minute and then comes back a little bit later as a different eigenvalue, and it's just a kind of cool back and forth that we can do. And if you didn't understand all that, that's okay. Maybe you already skipped forward in the video. That's okay too. You won't hurt my feelings. But we've got this here at the beginning and this here at the end. Okay, so I'm going to write those two guys next to each other. Lambda 1 times the dot product equals lambda 2 times the dot product. Okay, so what does that mean? Well, that means that lambda 1 minus lambda 2, so I'm subtracting them and factoring out the dot product, V1 dot V2. And since they're equal to each other, if I subtract that onto the left-hand side, well, then the right-hand side has nothing left on it, so that equals 0. All right, we're almost done. Thanks for sticking with me. And since that difference, lambda 1 minus lambda 2, cannot equal 0, the dot product must. V1 dot V2 must equal 0. It has to. How do I know that the dot product, or that the lambdas can't equal 0 when I subtract them? Way back at the beginning, they're eigenvectors. They're eigenvectors from different eigenspaces. So they're distinct eigenvalues, lambda 1 and lambda 2. If they're not the same number, their difference can't be 0. So cool proof. The goal here in going through that is kind of to start to understand the logic and how we work our way through a proof. This next theorem is pretty cool. I'm not going to kill you with a proof on it, don't worry. But what the theorem says is that an n by n matrix A is orthogonally diagonalizable if and only if it's a symmetric matrix. Okay, the significance, the cool factor here is that in Chapter 5, you had to do a lot of work before you knew if the matrix was diagonalizable, right? That's what we saw in Chapter 5. This theorem, if proven true, which it is, even though we're not going to do it, tells me if my matrix is symmetric, which I can tell really quickly by looking at it, I know it's diagonalizable, and not only that, it's orthogonally diagonalizable. Okay, so that's a pretty significant theorem that we can just immediately tell when it's diagonalizable. Okay, so we're going to do another example where we go through the orthogonal diagonalization. However, in this one, our eigenvalue of 7, oh, I didn't mean to circle the 7, it has a multiplicity of 2, and so that just throws an extra little kink in things here, right? So for lambda equals 7, right, we go through the typical process, and we get that V1 is the vector 1, 0, 1, and V2 is the vector, let's see, -0.5, 1, 0. And then for our other eigenvalue, lambda equals -2, we get the vector V3 is -1, -0.5, and +1, okay? And what you can immediately see is that V1 and V2, if you take their dot product, you do not get 0. You get -1/2. With that said, V1 and V3 take the dot product, and you do get 0. V2 and V3 take the dot product, and I think positive a half, negative a half. Yes, you do get 0. So V1 is orthogonal to V3. V2 is orthogonal to V3. But V1 and V2 are not orthogonal to each other. So can we still orthogonally diagonalize this matrix? The answer is yes, per the theorem. Okay, but we got to do a little tiny bit more work first. Okay, and what we're going to do is we're going to take V2 and orthogonally project it onto V1. V2 orthogonally projected onto V1, and we're going to use a different letter. We're going to call our orthogonal projection Z, and the formula, if you don't recall it from chapter 6, we take vector V2 minus this dot product over that dot product times that vector, right? And if you do that, you take your negative a half, 1, 0 vector minus the dot products give you negative 1/2 over 2 times the vector 1, 0, 1. And that all simplifies to negative a quarter, positive 1, and positive a quarter, 1/4. There we go. Okay, so V2, in order to get it to be orthogonal, we project it onto V1. And now, if you check, V1, Z, and V3, and now everything's just circled, but that's okay. Those three vectors are orthogonal to each other. Okay, so the remaining steps is to normalize. So now we normalize V1, Z, and V3. Normalize those three vectors, and then I can write down the P matrix in A equals PDP inverse, and that is 1, so I'm just giving the normalized vectors, 1 over radical 2, 0, 1 over radical 2, and then negative 1 over radical 18. That simplifies, that square root simplifies, but I don't have time for that. 4 over radical 18, and then 1 over radical 18. Negative 2/3, negative 1/3, positive 2/3. That's the P, and then D is my diagonal matrix 7, 0, 0, 0, 7, 0, 0, 0, negative 2. Cool. And then P inverse is the same as P transpose as we saw in example 2. All right, so just a little bit of extra work. We orthogonally project that vector when it doesn't already start out, when we have an eigenspace with a multiplicity of more than 1. Sometimes when using eigenvalues in math and also like in applications of math in the field and stuff, they refer to the set of eigenvalues as what is called the spectrum of A. So that's just a different word for the set of eigenvalues. And then we get this spectral theorem that sounds pretty cool, right? Just the name, it's called the spectral theorem for symmetric matrices. And if you have a matrix that is symmetric, it has these properties automatically. It has n eigenvalues, counting multiplicities, like we saw in the last example where it only had 2 eigenvalues, but one of them did have a multiplicity of 2. The dimension of the eigenspace for each eigenvalue equals the multiplicity of lambda as a root of the characteristic equation. The eigenspaces are orthogonal to each other in the sense that eigenvectors corresponding to different eigenvalues are orthogonal, and A is orthogonally diagonalizable. It's called the spectral theorem. It just generalizes kind of what we saw in the couple examples so far that we've gone through. And then the last thing that we do in this section is called a spectral decomposition, which is really just a different way to write A equals P times D times P inverse, but we're going to write that P inverse as P transpose because we're talking about an orthogonal decomposition of our matrix, of our symmetric matrix A. Okay, and so the way that we're going to choose to write this differently is I'm going to name the columns of P with a bunch of U's, U1 through UN. Those represent the columns of P. And then my D matrix, my diagonal matrix, is lambda 1, and then a bunch of zeros over to there, a bunch of zeros down to there, and then diagonally it goes down to lambda n. And then my U, my P transpose we're just going to write those U columns as U rows with a U1 transpose down to a UN transpose. Okay, so that's just the breakdown of our three matrices when we diagonalize. All right, and now what I can do is I can take these first two matrices, multiply them together, and what that simplifies to is lambda 1 U1 through lambda n UN. Right, that's what you get when you multiply the first two matrices, times U1 transpose through UN transpose. Okay, and then finally, last step in this problem is I'm going to multiply these two matrices together and get a different representation of A in terms of its eigenvalues. And the end product here is lambda 1 times U1 transpose plus lambda 2 times U2 transpose all the way through the end plus lambda n times UN transpose. So it is a decomposition of A, right? It's a factorization of A, decomposition, but it emphasizes the eigenvectors, eigenvalues first, and how A decomposes relative to its eigenvalues. Our last example has a lot of the work done for us, and we're just going to write down that decomposition, right? This I'm going to call, this is the P matrix, this I'm going to call U1, this I'm going to call U2. We can see that here's my lambda 1, here's my lambda 2, and this guy here is U1 transpose, down here is U2 transpose. Okay, so the decomposition looks like this. A, which is equal to the PDP inverse up above, is equal to 8 times U1 transpose plus 3 U2 transpose. I could even write those vectors in there if I wanted to. 8 times 2 over radical 5, 1 over radical 5, times 2 over radical 5 times 1 over radical 5. Plus 3 times negative 1 over rad 5, and then 2 over radical 5 times negative 1 over radical 5, 2 over radical 5. So it's a different, much different view than the PDP inverse up above, and the emphasis is on those eigenvectors, eigenvalues, and then the eigenvectors that follow them. Okay, called the spectral decomposition. It closes out section 7.1. It's the end of the video. Thank you very much for listening and have a wonderful day.